Hello, Math 2 Extended. This is Mrs. Bricky, and this video is for Math 2 Extended Unit 1, Lesson 1. We are going to be talking about function notation and exponents. Hopefully, those are both reviews for you. If you need some extra help in this topics, if you maybe were in a class that didn't talk about these last year, let me or Ms. Hurd know so we can help you. So functions are mathematical relationships where each input has exactly one output, and one common way to represent a function is symbolically, in other words, with an equation. You can also represent functions on a graph or on a table of values, but today we're going to just be focusing on symbolic representations, which is an equation. So functions will have a function name, like f is a really common function name, and that f literally is from the word function. So we've got f of, and then you'll see a set of parentheses with the input variable inside. So f of x means that our function's name is f, and the variable we're going to use to represent our input is x. And then it will be equal to, and it will give you some expression involving the input that's going to give you the rule for how to calculate the function's value, which is called the output. So I might have an equation like f of x is equal to 2x minus 5. That tells me that to calculate the function's output, I need to multiply the input by 2 and subtract 5. So for example, maybe I want to calculate f of 7. So I would sub in the 7 for x, and that means my output is going to be 2 times 7 subtract 5. And 2 times 7 is 14, subtract 5 gives me 9. So f of 7 is equal to 9. And for any input I choose, I'm going to get out exactly one answer. So the output that goes with 7 is 9. Function names can be logical. For example, in calculus, we often have velocity functions, so we use the name v, and for most of our velocity equations, our independent variable, our input is t for time. So we might have a function like v of t equals 7t minus 8 or something. One of the purposes of function notation is to help us work with multiple equations. For example, I might have 3 equations like f and g and h. Function notation is powerful because it tells you so much information. It tells you which equation you used. So I know when I see f of 7 equals 9, I know I used this equation. I know that the input is 7. So I know right away I'm talking about an x value of 7, and then I know that the output is 9. So it's just a lot more information than just saying y equals 9. And that 9 we can think of as a y value, but this notation just encodes so much more information than simply writing y equals 9. So we're going to work with these 3 equations. Whenever you're evaluating equations, if you have more than one, make sure you're paying attention to which function that you need to use, and then substitute in the appropriate input values. So if I have the equation, or if I'm asked to find h of negative 4, I know straight away I need to use the h equation, and I'm substituting a negative 4 in for x. So this function h tells us to multiply by 3. So if I multiply my input of negative 4 by 3, I get the answer negative 12. H of negative 4 is negative 12. So my next question right here says g of 1. So I know that in this case, I'm now using the g function. The g function has the x showing up twice. So the g function tells me to take my input and square it and then add the input. So I'm using that value of 1 twice in place of each of the x's. 1 squared is 1, and we're adding 1 to that. So we get that g of 1 is equal to 2. And then finally, I have f of n. Now this is different. It says that my value that I want to substitute for x is n. So I just literally put n into the equation, 2n minus 5. That probably feels a little bit silly. All we did was replace the x with an n, but that's exactly what we're doing when we're evaluating a function. Now, in a couple of days, we're going to look at more complicated situations, like maybe we want to sub in something like x plus 1. So this f of n is kind of just leading us towards some more complicated things later. It's also possible that we might want to know which input would lead to a particular output. For example, for h of x equals 3x, can you think of an input that would give an output of 15? So we're basically wondering which x value is going to give us this answer. And hopefully, mentally, you can just think about, well, that means that my x value is 5. So my input value, my x value is 5, and h of 5 gives me 15. I mean, if it's asking for an input value, this is your answer, but the way that you maybe get that answer is by thinking about this, that 5 times 3 gives you 15. It's not always possible to just mentally think of an answer, though, especially for more complicated functions. So let's look at the process for finding the correct input value. We're going to use function f. For function f, our function is 2x minus 5. Our first question is find x if f of x is equal to 7. So please note that this is not asking us f of 7. Definitely that is not what we're after. We're not substituting a 7 in. We are calculating the x value if f of x is equal to 7. So the way that you're going to do that, the procedure for when it's a more complicated function, is that you're going to take that function 2x minus 5, the equation of the function or the rule of the function, and set it equal to that output value that you're given. And now your goal is to solve for x. So in this case, if we solve for x, we're going to add 5 first. And then once we have that result, we're going to divide both sides of our equation by 2. And we get an x value of 6. Now that is my answer. If I wanted to check and see if it's true, I could calculate f of 6. F of 6 is 2 times 6 minus 5. Well, that's 12 minus 5. That is 7. So that's just a little mental check. Sorry, my equal sign looks kind of bad there. But this is just sort of checking to see if it works. So if you're ever like, I don't know, that seems like it might be right, but it might not be right, you can always kind of check your answer here. So this next one says find x if f of x is equal to negative 11. Anytime you're working with negatives, make sure you're being just a little extra mindful because most of our errors in math come from improperly dealing with negatives. So this is a new equation, but it's kind of the same procedure. We're going to add 5 to start. And now we have 2x is equal to negative 6. Again, be careful with negatives. And then we're dividing by 2 to find our input value, x equals negative 3. And that's my answer. If I wanted to check it, I could substitute in and make sure it's correct. All right, let's try this one. Example 4, for the function g of x is equal to x squared plus x, can you find the input that results in an output of 42? So our little setup is going to be, we're wondering when does x squared plus x equal 42? Now, this one, maybe you're thinking to yourself, my gosh, like what? How do I get the x by itself? This is an equation type called a quadratic equation, and we are going to learn all about how to solve these this year, but right now you don't have a procedure for that yet. So my goal was just for you to play around with numbers and see if you can figure out there's actually 2 x values that make this equation true. One of them is positive and the other one is negative. So if you have a second, pause the video, see if you can find those, and then I'm going to put up what those 2 answers are. So make sure you pause if you're going to try to figure it out. Okay, so the positive x value that makes this equation true is 6. That's because 6 squared plus 6 is equal to 42. So that works. And then there is a negative number as well that makes this equation true. The negative number is -7. And that's because -7 squared plus -7 is equal to 42. That -7 squared is positive 49, and then we're subtracting 7 to get 42. For the video, I'm not going to talk about a super bonus challenge problem. Come to class, though, and we talk about those. Okay, all of the functions we have worked with today have been polynomial functions. Polynomials are expressions that can be written as the sum or difference of one or more terms, each term being a product of numbers or variables. So, polynomials might have exponents. So you can see this one has an exponent right here, and this one has an exponent. If a polynomial has an exponent, it has to be a positive whole number, like 2 or 3. If a polynomial has coefficients on the variables, here's a coefficient, those coefficients can be fractions, they can be decimals, that's fine. The powers have to be whole numbers, but the coefficients can be really any type of number. In fact, this 2/5 here, that this could also be written as 0.4 y to the third, and that would be okay as well. So decimal or fraction coefficients are fine. Now, the definition is kind of, math definitions can kind of be pretty crazy. Terms are, let me show you what term means. A term is a little product. So like this is a term, this is a term. It's just a part of an expression. And terms can be, for polynomials, terms are products of numbers and or variables. So 3x squared is 3 times x times x. That's a little product. That's a term. 2x is a term. And it can just be a constant term like -5 or 7. Those are okay as well. So each of those chunks is a term. This is a single term. And terms are always separated by addition or subtraction. So, sorry, my computer's being a little funny. So we've got the terms being added or subtracted right there. And this one also is just a single term. Now this one, sometimes people are like, wait, I see division coming up. But this is kind of just shorthand. What this really means, or maybe a better way to view it, is that it's half of t or 0.5 t. So it is really no different than this one. It just sometimes, if the numerator is 1, it'll get shown as a divide by a number. So polynomials, sometimes it's hard to like really get a feel for what a polynomial is. So we're going to look at some things that are not polynomials and talk about the reason that they're not polynomials. So polynomials can't have division by a variable. That's not going to work. So this is not a polynomial because it has a divide by x. This is not a polynomial because it has a divide by t. Both of these two that I've highlighted, they belong into the rational function family instead of the polynomial function family. So those are not polynomials. This first one is not a polynomial because it has oops, I want that to be yellow, sorry, because it has a negative exponent. We can also not have a fraction exponent, so this last one is not a polynomial because of the fraction exponent. And we also can't have a variable in our exponent, so this one is not a polynomial right here because of the exponent that has the x in it. The 5 in the exponent is not a problem. It's the x that causes it to be not a polynomial. So we can't have division by a variable. We can't have a negative, a fraction, or a variable exponent. For polynomials, the exponents have to be positive whole numbers. And then our last requirement is that we can't have roots or other operations. Only addition, subtraction, and multiplication are allowed. So this one is not a polynomial because it has a square root of x. This one is not a polynomial because it has an absolute value function operator there. And we will work with absolute value functions later this year, and we will work with square root functions a little bit, but they are not polynomials. Okay, so you should have enough information to do the front side of the pink assignment. I'm going to continue the video, but if you want to pause and work on the front side of that assignment, you can. The rest of the lesson is about reviewing exponent rules. So for purpose of the video, I'm going to kind of do these really quickly because I think you probably are very familiar with exponent rules. If you have something like t squared times t to the 5th, that really just means that you have t times t times t times t times t times t times t, which is the same as t to the 7th. And if you ever can't remember your exponent rule, you should expand and sort of think about what that implies. So if you have a base like a with a power m and you're multiplying it by a base a with a power n, the exponent rule that you need to use is that the two exponents are added together. So this one would be x to the 8th. This one would be y to the 5th. If you have a situation where you have an exponential expression like w squared and it's raised to the 5th power, that really means that you have a w squared, or in other words, a w times a w, multiplying by itself 5 times. So w times 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 w. And that's really just w to the 10th. So if you think about expanding these, you maybe can see that the exponent rule is that we multiply. If we have a power raised to another power, we multiply those powers together. So this next one would be x to the 15th power because we have 15 x's multiplying together. And this one would be y to the power of 6. So hopefully you remember those exponent rules. And we had a little matching activity. So we've got an x to the 3rd multiplied by x squared. So that would be x to the 5th. So I would challenge you to kind of stop the video, do these, and then you can match up and see if you did them right. So pause if you want. This one is x to the 6th because we multiply those powers together. This one is x to the 14th because we multiply those powers together. This one is x to the 8th because we have x to the 7th and we're multiplying it by one more power of x. So that's x to the 8th. This one would be x to the power of 10. Here we have x to the 7th multiplied by x to the 0. So if we add those powers together, it is just x to the 7th. Now, what that means, you might recall, that means x to the 0 is equivalent to 1. The next one here, x squared raised to the 8th power, that's a situation where we need to multiply those powers together, x to the 16th power, and then our last one is x to the 9th. And then here's those exponent properties again. So if you have a situation where you are adding variables together, like a plus a plus a, that is going to change the coefficient. We have 3 a's. When you have a situation where you are multiplying variables together, like a times a times a, that is going to change the power. We represent that with a to the 3rd. Okay, super important note about exponents. Really just trying to address here some common errors that occur. An exponent applies to the number or variable that is immediately to its left, and that number is called the base. So if you have something like x squared, that means that we have x multiplied by x. And the base is x, and it means to times an x by another x. If we have 5 to the third, the base is 5, and it means that we're timesing by 5 3 times. We've got 5 times 5 times 5. People are usually pretty darn good at understanding that. But sometimes when we have a more complicated base or when we have a grouping symbol, it can start to confuse people, or people can assume a grouping symbol that is not there. The exponent applies to what is immediately to its left. So if the thing that is immediately to its left is the number 4, that means that the exponent applies to the number 4. In this case, it does not apply to -4. The base is 4. This expression, and if you type this into your calculator is doing -1 times 4 times 4. It's using 4 as the base, and your calculator is going to give you the answer -16. But if you look at the one below, the thing that is immediately to the left is a grouping symbol. That means the exponent applies to that whole group. So that means that the base is -4. And when I square it, that means what I'm doing is a -4 multiplied by a -4. So this second one is +16. So you need to know when you're typing into your calculator what you want the calculator to do, and you need to communicate that to the calculator effectively. So if you are doing a function like x squared and you want to substitute in -5, you need to type it in like this. If you have a function like -x squared and you want to substitute in a -5, it might look like this. This one will give you a positive answer. This one's going to give you a negative answer. We're going to be working a lot with quadratics this year, so we're going to get good at this. And knowing like how to avoid calculator errors and to mean what you say and say what you mean when we're dealing with substituting negatives and powers with negatives. On this next column over, we have a similar situation with a coefficient of a variable squared. So in this first case, if you have 7x squared, the x is what is squared. Not a 7 squared, just the x is squared. So the base is x. This means 7 times x times x. And so we really can't like do anything to change it or simplify it. In the next example down, the thing immediately to the left of the exponent is a grouping symbol. So the base of this second one is 7x. And so when I square that, that's 7x times by 7x, that's 49x squared. So make sure you are really paying attention to, what the base is and making sure to try to avoid calculation errors. Okay, that's it. You should have enough information now to finish the back of the assignment as well. If you have any questions or anything, let me or Ms. Hurd know. Thanks so much.